All right, so graphs of quadratic functions. These are all the things that hopefully we already know about. So we know that in a graph of a quadratic, it's going to be the shape of a parabola. Right? Our parabola is either going to be smiling or frowning, depending on what our A is. Right? So it's either concave up or concave down. We know that our parabola is symmetric about the line x equals negative b over 2a, which we call the axis of symmetry. And I think I'll create this graph bigger. Let me erase that for now. We know that we can find the vertex by whatever that x value is from our axis of symmetry, would be your x coordinate of your vertex. And then to find the y coordinate of your vertex, we would just plug in whatever that value is into the function. Right? So my x is the negative b over 2a. The y value would be whatever my function is evaluated at, negative b over 2a. We know our y-intercept is the ordered pair 0, comma, whatever f of 0 is. So when we plug in 0 for our x, what's my output? That would be your y coordinate. And then your x-intercepts, I used s sub 1. That's what our books use. So s sub 1, comma 0 and s sub 2, comma 0, or s of 1 and s of 2 are the solutions to your quadratic. Okay. So if we think about this as a graph, erase some of this and give myself some space. So everybody at least got the first three? Hopefully if not, shout it out. So if we think about a quadratic graph, let's make a rough sketch of a quadratic graph. So make a x and y axis there. I'm going to shift it over here. So there's my parabola. Oops, actually, let's make it have a y-intercept. There we go. Hopefully yours is more symmetric than mine. We know that our axis of symmetry is that line that goes straight down the middle. So if I were to fold it over, it would be the same on both sides. So axis of symmetry, which is the equation x equals our negative b over 2a. My solutions are the x-intercepts, which that right one would be of the form negative b plus the square root of b squared minus 4ac all over 2a, comma 0. The left side would be the negative version, so negative b minus the square root of b squared minus 4ac all over 2a, comma 0. And here we have our vertex. And then here I have my y-intercept, which is of the form 0, comma f of 0. Okay, so there is graphically. Nothing new, right? Now we just kind of have it visually there in front of us. All right, so everybody good? I'll give you 5 more seconds. Okay, so given a function, can we determine all of that information? Can we find the x and y-intercepts? Can we find the axis of symmetry? And can we find the vertex? So if my function is f of x is equal to x squared plus 2x minus 8, We want to be able to find all the intercepts, axis of symmetry, and the vertex. We won't graph it for this example, but then hopefully you should be able to then take it to a graph. So let's first start with the x-intercepts. So my x-intercepts means we need to solve it. How do you want to solve that quadratic? First, I would always check, is it factorable? Is it factorable? Are there factors of -8 that get us to 2? Yeah. +4, -2. So this factors to x plus 4, x minus 2 is equal to 0, which tells me my solutions are -4, +2. So my x-intercepts are going to be -4, 0, and 0, 2. Oh, yeah. Thanks. Doing some transitive property in my head there. Okay, so -4, 0, 2, 0. So now let's find the y-intercept. Well, y-intercept's easy. Just eliminate all the x's and we're left with what? The -8. So 0, -8. Axis of symmetry. Oops, I'm going to do AOS for axis of symmetry. Would be x is equal to -b, so -2. All over 2 times my a is 2, so -1. So my axis of symmetry is at x equals -1, which then puts my vertex at -1. If I plug in -1, -1 squared is 1, -2 minus 8, so -1 minus 8, so -9 would be your vertex. Okay? Easy enough. Given a function, we can come up with all that information. Then we could essentially just plot that stuff and graph it, right? Yeah? Rounds of heads. Yeah. Okay. All right. So we've got that. So now let's quickly talk about different graphs that we could have and the number of solutions that they could have. Now there's a rule that whatever your highest degree is of your polynomial, you must have that number of solutions. So if we have a quadratic, then I know that I have to have 2 solutions. Okay. So what would a graph look like if your function had no real solutions? Jalen? Yeah. It'd be kind of like hovering above your x-axis. So if you have no solutions, you have to have at least 2 solutions. So if I have no real solutions, that means I have to have 2 imaginary solutions. Right? And the complex conjugate theorem tells us that if 2 plus I is a solution, then its conjugate, 2 minus I, must also be a solution, which would be your 2 imaginary solutions. What would the graph look like if it had 1 solution? It would just be touching the x-axis at the vertex. So if I have 1 real solution, where does the second one come from? Can I have 1 real and 1 imaginary solution? No, because imaginaries always have a pair with them. So have you guys learned about multiplicities? No? Maybe? Yes? No? Multiplicities. So just as a sidebar, if you had, let's say that was at x is equal to 1, what would be the linear factor for x equals 1? It would be x minus 1. If I doubled that and put the 0 at it happening twice, and then multiply that out, that would get me x squared minus 2x plus 1. And then if I go to find that vertex, -b, so 2 over 2 puts me at 1. Then I would be at 1, what would that be? 1 minus 2, so -1. So 0, right? So that would be my vertex, which is on my axis of symmetry. So whenever you have duplicates or the same linear factor, we call that a multiplicity. So if I have one solution, because I know that I need to have two, you're going to have what's called having a multiplicity of two, which means that that 0 is just occurring twice, which means it's just you have two linear factors of that same 0 to get that quadratic. Does that make sense? So if I have 1 and 1, I just have it twice, but I need to have two of them there to make it into a quadratic. Because if I only had one, then I would have a linear function and not a quadratic. And then two solutions just means it's going to cross twice, which means you would just have two real solutions. You wouldn't have any multiplicities. You would not have any imaginaries. Okay, so because we're dealing with quadratics, I know I must always have two solutions. It could either be two reals. It could be one real with a multiplicity of 2. It could be no reals, which then means I have two imaginary. Does that make sense? Yeah? Okay. All right. So let's go ahead and jump to our calculators next. Let's make sure we can find the solutions of a quadratic on our calculator. So on your calculator, can you graph the 3x squared minus 9x plus 2? Freeze that and do it on mine. Y equals, do we feel like we're getting a little bit more comfortable with our calculators? Hopefully. All right, what was it? 3x squared, 3x squared minus 9x plus 2. Oh, I got a scatter plot on here. All right, so here's our graph. What am I going to do to find the solutions? I'm going to go to second trace to our calculate option. What do you think we're going to choose? Number 2, the zeros, right? We're looking for the zeros, which are your solutions, which are your roots. So same deal. We have to just make a left bound, right bound. Make sure you're on top, make sure you're on the bottom. Don't worry about guessing. So one of our solutions is, what did it say we were rounding to? The nearest tenth, so 0.2. And then if I need to find the second one, I'm going to do another second trace, number 2. And then come from below, hit enter, get above it, hit enter. Don't worry about guessing, and we have 2.8. So my answers were, that 0.2 and, what did I say, 2.8? So our solutions were x equals 0.2 and 2.8. Okay, is everybody able to do that on their calculators? Find zeros? Hopefully. Okay, so given a quadratic, we can find x-axis, or axis of symmetry, vertex, x-intercept, y-intercept. We know what a graph looks like with no solutions, one solutions, two solutions, and we know how to do this on our calculator. Got all that covered so far? Okay, so now we're going to move to what's called vertex form, which is all of our completing the square stuff. So vertex form, if you guys remember from last year, the reason why we like vertex form is when we think about all of our transformation movements of parent graphs, if I have a quadratic in vertex form, I can easily graph it using the idea and concepts of transformations that we had before. Okay, so if I can get my quadratic to look like this, so f of x is equal to a times the quantity x minus h squared plus k, I now know that my vertex is going to be the coordinates of h comma k, and my axis of symmetry is going to be x is equal to h. Because if we remember, That minus h is moving us right or left. Our k is moving us up and down. So my parent graph is putting me at 0, 0. So if this was x plus 2, then I would be shifting left 2. If this was plus 1, I'd be shifting up 1. So my vertex would be at negative 2, 1. If I go back to 0, 0, if this was minus 2, that shifts me to the right 2. If it was plus 1, go up 1. Now my vertex is at 2, 1. So if you have it vertex form, then you can easily just graph it using your idea of transformations. Okay? All right. I don't think we need all of that. That's just the same. So let's go ahead and do this into our vertex form. So we've got the function f of x is equal to negative 2x squared plus 4x plus 3. We want to rewrite it in vertex form. And then use that to describe our different types of transformations that we have. Let's just go back. I was trying to make it easier and we made it harder. So if we complete the square, let's just do that. I was trying to just pull out the 2. Let's just stick to what we know. Dividing out the negative 2 everywhere. Divide out, divide out, divide out. So then we get x squared minus 2x plus blank is equal to 3/2 plus blank. All right, completing the square process. We're back in familiar territory. Okay. What's my plus blank? Well, it's my b divided by 2, which is negative 1. Negative 1 squared is 1, so we're going to add 1 to both sides. So the left side is x minus 1 squared is equal to 5/2. Shifting that over gets me, I'll move over here, I'm running out of space, gets me x minus 1 squared minus 5/2 is equal to 0. So now if I think back to the original problem, I know that that parabola should be concave up or concave down. Down, right? Which means my a needs to be positive or negative. Negative. So right now I need to get rid of my fraction of 2. But for my a to be a negative 2, I need to multiply everything by a negative 2. So then I would end up with negative 2 times the quantity of x minus 1 squared plus 5 is equal to my function, which is the answer we needed. Stick to what we know. Don't get fancy. Is that a good rule of thumb? So what would be the transformation? The minus 1 tells me that we're going to be shifting to the right 1. We're going to go up 5. We're reflecting over the x. X-axis. And then what's that 2 going to do? Vertical or horizontal? Vertical, stretch or shrink? Stretch. Good. So vertical stretch by a factor of 2. All right. Let's just stick to what we know. Should we do another one of these just to make sure we have it? Be nice, like, no. All right, so we've got that. Maybe we'll just stop there and we'll save the transition curves for next class.